to the Curious Calculator. In today's video, we're going to be going over independent versus dependent events and when order matters versus when order does not matter. Alright, so to get started here, let's start with independent, which is when we have replacement. And so, looking at the first example here, we have order matters for this one. So let's read through it. You draw 5 cards from a deck of 52 cards while replacing each card. What is the probability that you draw 1 heart followed by 2 clubs followed by 2 diamonds? Alright, so let's get started with calculating the probability here. So we want to, out of a deck of 52 cards, draw 1 heart, then 2 clubs, then 2 diamonds. So we can begin here with the probability of drawing 1 heart out of 52 cards is, let's see, well, we got to keep in mind that there are, in a deck of cards, there's going to be 13 hearts, 13 clubs, 13 diamonds, and 13 spades. So I'm going to go ahead and just write that right here real quick to keep that in mind. 4 suits, whoops, there's going to be 13, I'll just say D for diamond, 13 hearts, 13 spades, and 13, let's see, clubs. Okay, so if we're going to draw 1 heart out of 52 cards and there are 13 hearts, that means that there are, let's see, 13 favorable outcomes. So 13 favorable outcomes over the total possible 52 outcomes, or 52 cards. And so we're going to do that for our first one. That's going to be the probability of drawing 1 heart. Then we want to draw a club. And let's keep in mind here that we put that heart back into the deck. So we still have 52 cards. And so let's see here. There's going to be 13 clubs total in the deck. So again, that's going to be 13 out of 52 because we have 13 favorable outcomes out of the 52 possible outcomes. And then we want to draw a club again. So we also, let's keep in mind we put that club back in the deck. So we still have 52 cards and there are still 13 clubs. Okay, so now we've done that. Now we want to do 2 diamonds. So again, we put those cards back. So there's still 52 cards. And let's see, we have 13 diamonds. So there are 13 favorable outcomes out of the 52 possible outcomes. And then we want to do that again. We want to draw a diamond again. So again, we're going to have the 13 over 52. And that right there will give us the probability of drawing 1 heart followed by 2 clubs followed by 2 diamonds when we're replacing each card that we draw. Okay, so now let's contrast this or compare and contrast this with the next example where order does not matter. So this one, you draw 5 cards from a deck of 52 cards while replacing each card. What is the probability that you draw 1 heart, 2 clubs, and 2 diamonds? Okay, so one thing I want to say here is that when we talk about order matters and order does not matter, I think it can be a bit confusing in that, well, order does matter in a sense when you're calculating probability because we're looking at a particular arrangement, like in the first example here, where we're drawing 1 heart followed by 2 clubs followed by 2 diamonds. So that's the arrangement we're looking at is heart, club, club, diamond, diamond. And so that is why we say order matters, because we are considering only that particular arrangement. But what we need to know is that it doesn't matter let's say I instead had club, club, heart, diamond, diamond, or let's say we had club, heart, club, diamond, diamond, any of these. So all of these, although they are different arrangements, as we can see, they still contain the same cards. So each of these arrangements, although different, all have one heart, two clubs, and two diamonds. And so the probability of getting any of these arrangements is going to be the same. It's going to be the probability of drawing just one heart, two clubs, and two diamonds in general. But we say that the order matters here because we are really concerned with just finding the probability of drawing the one heart, the two clubs, and the two diamonds in this particular order. So in essence, what we're doing is we're finding the general probability of drawing one heart, two clubs, two diamonds, and multiplying that by the one particular arrangement we're interested in, and that is giving us our probability when order matters. Okay, so now let's look at the next one. And so that's what we just discussed there is going to help us understand why we can do what we're about to do with this one. And so when we have that order does not matter, we just want to know what's the probability of drawing one heart, two clubs, and two diamonds in any possible order. We're going to find the probability of drawing the one heart, two clubs, and two diamonds in general, which is what we found above, the 13 times 50, 13 over 52, 13 over 52. So I'm just going to copy down what we found in the previous problem. And then, so this is the general probability of getting those cards. And then what we want to do is we want to multiply this by the total possible arrangements, because now we're not just concerned with one particular arrangement where we can, I'll just write, we can imagine that we multiplied this by 1 because we cared about this particular arrangement. But now we care about all the possible arrangements we can get. So we're going to have to multiply this by those possible arrangements. And now let's talk about how we can find the total possible arrangements we can have. So if we have 5 cards, we can, let's do it like this. We have 5 slots. And we want to know the total possible arrangements of having one heart, 2 clubs, and 2 diamonds. Well, let's first find what are the total possible, or the total number of ways that we can place 5 different cards in these 5 slots. So let's think about it like this. In the first slot, I have 5 cards in my hand, and so I have 5 different options of cards to place in this first slot. Now I'm on the second slot. I placed a card down, so I have 4 cards in my hand. So there are 4 possible cards now that I can choose to put in this slot. And then again, now I have 3 cards, and so I have 3 possible cards that I can choose to put in this slot, and so on. 2 and 1. Until I only have 1 card left in my hand, I just have to put it in that last slot. But now we want to keep in mind is that this may look something like, well, let's consider, let's say this just looks like heart, club, club, diamond, diamond. Well, then what we need to consider is that these 2 clubs are the same. Whether I have this club here, I'll just say this is club 1 and club 2, and I'll label this one D1, D2. Whether I have this club 1 here or this club here and vice versa, it doesn't matter. Those 2 arrangements, so I'll actually just write right here. So H, C2, C1, D1, D2, This we are counting as the same arrangement as the one right here. And so we want to account for that whenever we're counting the total possible arrangements. And so let's see here. What we need to do is well, I'm going to actually do this multiplication out. This 5 times 4 times 3 times 2 times 1 is the same thing as 5 factorial. And then what we need to think about is dividing by the different arrangements that are identical. And so what we can think about is like in this example, the number of identical arrangements with this one is going to be the different ways that we can arrange the C1 and C2, which we can think of if we have 2 cards. What are the different ways that I can arrange these 2 cards? Well, I have 2 cards in my hand, and so for the first slot, I have 2 options. Now I only have 1 card in my hand, so I only have 1 option left. So the possible number of ways to rearrange 2 cards would be 2 factorial. And so for this arrangement, I need to count for that, and I need to divide by that 2 factorial here. But then we got to think, well, we also have these diamonds that are identical. And so if we rearrange them in a different way, let's just say we had H, C1, C2, D2, D1. This counts as the same as this one and this one. It doesn't matter if we flip the different clubs around or the different diamonds around. Those are still going to count as the same arrangement. So again, we need to divide by the different amount of ways that we can place those 2 diamonds. And so that again is going to be the 2 factorial. And then the heart, well, there's only one of those cards, and so the different number of ways you can place 1 card, well, we can write that here, although it is a little trivial and you often may not see it, but that's going to be 1 factorial. And so what this comes down to is this is equal to 5 factorial over 2 factorial 2 factorial. And so that is the total number, the number of possible arrangements. And now we need to multiply that by our general probability here. So we have times 5 factorial over 2 factorial over 2 factorial. Okay, awesome. So we finished up that one. And now let's go on to the next examples we have here. And I'm going to kind of just draw this little line here so we can have a little separation. Okay, so now we're going to be talking about dependent events, and that's when there is no replacement. So in this first one, order matters. So you draw 5 cards from a deck of 52 cards without replacing them. What is the probability that you draw 1 heart followed by 2 clubs followed by 2 diamonds? And so let's go ahead and do that. If we draw 1 heart and there are 52 cards, again there are 13 hearts in the deck. So that's going to be 13 over 52 favorable outcomes to total possible outcomes. And now we're not going to put that card back into the deck. And so that means that now there are going to be 51 cards in the deck, 51 total possible outcomes. And so we have 51, and now we want to draw a club. And so let's see here, clubs, because we drew a heart and not a club, there are still 13 clubs in the deck. And so we have 13 out of 51. And we're not going to put that back in there. And so we have 50 total possible outcomes. And because we just took a club out, rather than there being 13 clubs in the deck, there are now 12 clubs. So now we have 12 favorable outcomes out of the 50 possible outcomes. Okay, and now we want to draw a diamond. And there are going to be 49 cards in the deck now, 49 possible outcomes. And there are 13 diamonds still in the deck. And so we have that. And then we have, well, we didn't put the diamond back in, so there are 12 diamonds now out of 48 cards. And that right there will be the probability for that case. And again, let's point out here that this probability right here is equal to the general probability of drawing one heart followed by two clubs, or no, I'm sorry. It's the general probability of drawing one heart, two clubs, and two diamonds multiplied by the one single arrangement that we care about in this question, which was the heart, club, club, diamond, diamond. So you can imagine this as being multiplied by 1, corresponding to that one particular arrangement we care about. Okay, so now when we do order does not matter, you draw 5 cards from a deck of 52 cards without replacing them. What is the probability that you draw one heart, 2 clubs, and 2 diamonds? So what we're going to do is we're going to use the general probability of drawing one heart, 2 clubs, and 2 diamonds, which we just found in the previous problem here. So we can go ahead and copy that down. 13 over 52, 13 over 51, 12 over 50, 13 over 49, and 12 over 48. And we're going to multiply that general probability times the number of different arrangements that we can have, which is going to be the same as what we found in the previous problem. It is going to be the 5 factorial over 2 factorial times 2 factorial. And that is found in the same exact way that was described earlier on. And so now we're going to multiply that by the 5 factorial. Let's see, 5 factorial over 2 factorial 2 factorial. And that right there will give us the probability for that case. All right, that is going to wrap up today's video. I'd just like to end with a little fun fact from philosophy. Did you know that Immanuel Kant argued that the universe is not necessarily ordered, but rather the order that we see in the universe is a result of our mind and reason putting a conceptual structure or applying a conceptual framework to the world, which ultimately results in the world having this ordered and structured appearance.